Hey everyone, it's Japoo, and today we're going to be talking about the Fundamental Theorem of Calculus, or Antiderivatives. Just a reminder, if you want to follow along to this video, the worksheet that I'm about to do and the answer key are linked in the description below. So the first thing I wanted to talk about was what exactly the Fundamental Theorem of Calculus is. Basically, it's kind of the rule that tells you how to take antiderivatives. When you have an integral, you're basically taking the reverse derivative of whatever function is in the integral. So to evaluate an integral, what we're going to do is take the function inside the integral. We call that the integrand, and then take the antiderivative of that function, the reverse derivative of that function, if you will. So for example, we know that the derivative of f is f prime, but that means that the antiderivative of f prime is f. So we can kind of see that in this equation right here that tells you what ftc is. So f prime is our integrand. It's our function that we're taking the antiderivative of. And you can see that once we've taken that antiderivative, we get f. So f prime's antiderivative is just f. You can see that we've replaced the x's with b and a here, and that's because we're plugging in the two numbers on the integral. So what you're going to do when you have two numbers on your integral is you're going to plug in the top number to your antiderivative, and then you're going to plug in the bottom number to your antiderivative, and you're going to subtract the bottom from the top. So it's going to be top minus bottom. The other thing that I wrote down on this worksheet just before we started is the power rule when it comes to integrals. The main antiderivative taken on this worksheet are taken from polynomials or things with numerical exponents. So x to the fifth or something like that, x to the fifth power, x cubed, x squared, that kind of stuff. And this is the rule that we like to use. It's basically the reverse of the derivative power rule. So for the derivative power rule, obviously you drop the power and then subtract 1 from the exponent. So x squared would be 2x, right? Now, the integral power rule is a little bit different. For the integral power rule, what you're going to do is add 1 to the exponent. So you can see right here, we're adding 1 to our exponent, and then divide by that new exponent or multiply by the reciprocal, and that's what this indicates. We have a plus c here because we don't have numbers on our integral, but for this worksheet, we are going to have defined integrals, so we don't have to deal with plus c. Alright, so let's try a few examples. Hopefully this will make a little more sense when we actually put it into practice. So let's start with our first one. We have 2, right? This is kind of a little tricky to think about as in terms of power rule, but if you think about 2 as being 2 times x to the 0 power, then that makes it a little easier. So anything to the 0 power is 1, right? So 2 times 1 is 2. But if we want to take the antiderivative of 2, we're going to have to, if we're going to take the antiderivative of 2 times x to the 0 power, we add 1 to the exponent. So we're going to add 1 to 0 and then divide by that new exponent. So what we're going to do is we're now going to have 2 times x divided by 1, which is just 2x, right? And we can kind of check our work to make sure that we took the antiderivative correctly, because if we want to take the derivative of 2x, we get 2, right? So that's kind of how we know. We know that 2x is the antiderivative of 2, because if we reverse that process, we do get a derivative. Then we're going to plug in the top of the integral and the bottom of the integral into our antiderivative. So that's what that vertical bar means. We're just plugging in. So then we're going to get 2 times 5, which is 10, minus 2 times 0, which is 0, and our answer is 10. Let's start with the next one now. That one was pretty easy. This one's a little bit more tricky. And it's also kind of easier to actually see the power rule in this case. So in our integrand function, we have 5x minus 1, right? So what we're going to do is add 1 to the exponent of x. So that's 1 plus 1, 2. So our new exponent for x is going to be 2. And then we're going to divide that, that expression by 2. So we now get 5 halves times x squared. And then kind of a similar thing that we did in number 1, we're going to have x as our antiderivative for 1, because 1 is technically 1 times x to the 0 power. So if we add 1 to 0, we get 1, which is just x. So 1 times x to the 1 is just x. Once we have that expression, our antiderivative, we can go ahead and plug in the top and the bottom. Be careful with parentheses on all of your top minus bottom steps, because that can get a little bit tricky, but make sure that you have all of your top and minus all of your bottom. Like, you want to do the individual math parts first and then subtract. So we're going to get 129 over 2 as our final answer. And see how, again, I put the parentheses around the top, the parentheses around the bottom to kind of distinguish the top minus the bottom. Okay, number 3, again, very similar. We are going to do the power rule first. So we have t cubed, and so we're going to add 1 to the exponent. We're going to have 3 plus 1 is 4, so we're going to have t to the 4, and we're going to divide that by 4, because we're dividing by our new exponent, which cancels out this 4 in front of the t, giving us t to the 4 power. We're going to subtract that by 2 times t cubed, because t squared is our original function, and to take the antiderivative of t squared, we're going to add 1 to 2 to get our new exponent 3, and then divide the entire thing by our new exponent 3, which will give us 2t cubed. Now we're going to plug in. And again, we want to be careful with our parentheses. I accidentally wrote an x here. It doesn't really change the outcome of the problem. It's just an issue in notation. Technically, this x should be a t, since t is our variable in this case. But what we're eventually going to get is the top minus the bottom. So I'm going to plug 1 into our antiderivative and close that off in parentheses. And then I'm going to subtract it by the antiderivative with 2 plugged in to all of the t's. And then we're going to get a final answer of -1. All right, moving on to number 4. Number 4, we do have to do a little bit of rearranging before we can actually get to taking the antiderivative. As you can see, we have a square root of y right here. And we actually want to use the power rule as much as possible, which means that we're going to rewrite square root of y, so we have y to the 1/2 power. I know what you're thinking. We might want to rewrite 3 over y too, right? So we can keep using the power rule properly. Actually, the power rule does not work when n is equal to -1. When the power is equal to -1, as it is in 3 over y. Because the antiderivative of 1 over x is ln of x, since the derivative of ln of x is 1 over x. So 3 over y is actually going to be, the antiderivative of 3 over y is actually going to be 3 ln y. So we don't need to rewrite that. So if you ever see a variable with a power of -1, that is going to, your antiderivative of that will be an ln. So you do not need to kind of manipulate that so you have a straight power that you can follow with the power rule. However, for square roots or like 1 over y squared or something like that, you do want to go ahead and change that into a variable to the something power just to make it easier on yourself. So as you can see, we did that for square root of y. We changed that to y to the 1/2 power. And then we take the antiderivative of that. So we add 1 to 1/2, which gives us 3/2. And then we divide by 3/2, which is essentially the same as multiplying by the reciprocal of the fraction. So we get 2/3 y to the 3/2 plus 3 ln y, because as I said earlier, anything that's like 1 over x is going to be an ln, because the derivative of ln of x is 1 over x. So since antiderivatives are basically the reverse derivatives, 1 over x, 3 over y, anything like that is going to be an ln of the variable. Now we get to plug in our top minus bottom. Be careful of the variables again. And as you can see, I accidentally messed up the notation again. This x should be a y. It's not going to change your answer. It's just an issue in notation. Okay, so now that we're plugging in, we're going to have 2 over 3 times 9 to the 3/2 plus 3 ln 9. That's our top. And we're going to close that all in parentheses minus, and we're going to have another set of parentheses, 2 over 3 times 1 to the 3/2 plus 3 ln 1. Now let's do a little bit of math. I want to clarify that 9 to the 3/2 is essentially the same thing as 9 to the 1/2 and 9 cubed. Kind of. So what we want to do first is apply the bottom number to our 9 and then the top. What that means is we want to take the square root of 9 first and then cube the square root of 9, which gives us 27 as our answer. I'm also just going to go ahead and cross out 3 ln of 1 because the ln of 1 equals 0, so 3 ln of 1 is going to equal 0 in this case. So that's ultimately going to get us 54 over 3 plus 3 ln 9 minus 2/3, which will equal 52 over 3 plus 3 ln 9. This problem was a little bit trickier than our first three, just because we had to rearrange the equation and recognize that we had an ln situation. So be on the lookout for that in these next couple of problems. Number 5, as you can see, again, we're going to have to rewrite the equation because we do want to put it in a form where we can apply the power rule. We're using the power rule in this case because it's 1 over t squared, making the exponent in this case -2. If it was just 1 over t, we would have left it as is and just converted that into ln of t. But since it is 1 over t squared, we're going to change it to t to the -2. So once we rewrite that, we can actually go ahead and use power rule. We're going to add 1 to the exponent, so -2 plus 1 gives us -1, and then divide the entire expression by that new exponent, divide by -1, which gives us -t to the -1 power. Now that we've done all of that, we can finally go ahead and plug in our top and bottom numbers on our integral, which is going to give us -1/2 plus 1 equals 1/2. So this is our top minus our bottom. I just put an addition sign because we're subtracting a -1. So the minus sign and the negative cancel each other out, and make it a positive 1. And our final answer will be 1/2. All right, number 6. As you can see, we have an exponent of -4, but it's at the bottom of the fraction right now, so we actually want to rewrite so we can use the power rule. So our new integral is going to be 2 plus 3x to the -4. Again, we're just rewriting 3 over x to the 4. Okay, once we do that, we can go ahead and plug in. So we're going to have, oh wait, first we have to take the antiderivative before we can plug in. So the antiderivative of 2 is 2x. We went over this in problem number 1. And then we're going to have -4 plus 1 for the 3x to the -4, since we're adding 1 to our exponent. And then we're going to divide our expression by a -3, since -3 plus 1, or -4 plus 1 is -3. So our new exponent will be -3, and then we divide the entire expression by -3. That's going to give us -3 over 3x to the -3 power. And 3 divided by 3 is 1. So we can kind of simplify that to give us 2x minus 1 over x cubed. And as you can see, I just got rid of that negative power since we finished with the power rule and moved that back down to the denominator of the fraction. Now we can plug in. So we have 3 and 1 to plug in. So that's going to give us 6 minus 1 over 27, close parentheses, minus another set of parentheses, 2 minus 1. And that's all going to equal 162 over 27 minus 1 over 27 minus 1, which will eventually give us 134 over 27. So in number 7, you can see we have a trig function, so we're actually not going to use the power rule since we don't have any exponents. I like to think of trig function antiderivatives as just like the reverse of the derivative rules. So when I see negative sign x, essentially, I kind of think, oh, what would -2 sine x be the derivative of? What function's derivative is negative sine x? And as you can see, I've already kind of started writing it here, but it's going to be cosine x. The derivative of cosine x is negative sine x, which means that the antiderivative of negative sine x is cosine x. So our antiderivative in this case would be 2 cosine x. We're then just going to go ahead and plug in 0 and negative pi, which will give us 2 cosine 0 minus 2 cosine negative pi. And that's going to give us 2 plus 2, which leaves our final answer as 4. See if I can get it. Nope. Okay, I guess not. But the this 2 comes from this first part, the top. So cosine of 0 is 1, so 2 times 1 is 2. Cosine of negative pi is -1, so that would be essentially a positive 2 eventually when the negative sign and the minus cancel each other out. 2 plus 2 gives us 4 as our final answer. All right, now moving on to number 8. So your teacher might make you memorize the antiderivative rules, which could be useful in problems like number 7 where you have a trig function. Although I also find it easy enough with simple kind of antiderivatives to kind of reason it out. So if your teacher wants you to memorize the antiderivative rules, you definitely should. And if you find that kind of reasoning the antiderivative from the reverse derivative is too complicated of a process, I would recommend memorizing the antiderivative rules also. It's easy, it's not too difficult, it's very similar to the derivative rules because it's like almost exactly the same as the derivative rules except reversed. And you can always use kind of thinking about derivative rules in reverse to help you with any antiderivative. So in this case, we're actually not going to be using the power rule again because we have negative e to the x and 5 to the x. So the antiderivative of e to the x is going to be e to the x, since the derivative of e to the x is e to the x. The antiderivative of 5x, well, let me just tell you the rule. So the derivative of a to the x is going to be a to the x over ln a. So in this case, since we have 5 to the x, our antiderivative is going to be 5 to the x over ln of 5. We're then going to plug in 1 and 0, and then just kind of do our top minus bottom. So we're going to have negative e to the 1 power, which is just negative e, plus 5 to the 1 power, which is just 5, over ln 5 minus, so all that's in parentheses, and then we're going to do minus negative e to the 0 power plus 5 to the 0 power over ln 5. I want to remind you that anything to the 0 power is going to be equal to 1. So e to the 0 will be equal to 1, and 5 to the 0 will be equal to 1. So our final answer is just going to be negative e plus 1 plus 4 over ln 5. Right, that's pretty straightforward. Number 9, we will also not be using the power rule. We are going to kind of be looking at trig functions. So if you've memorized your antiderivative rules, that's fine. You can just use those that memorization here. Or if you want to kind of reason it out, we can do that as well. So when I look at this, I'm thinking kind of what is secant theta tan theta the derivative of to find the antiderivative. So if you recall your derivative trigonometry rules, you know that secant x is equal to secant x tan x, the derivative of secant x is equal to secant x tan x, and that basically means that the antiderivative of secant x tan x is going to be equal to secant x. So in this case, the derivative, or the antiderivative of secant theta tan theta is just going to be equal to secant theta. And then we're going to plug in pi over 6 and 0, which will give us secant pi over 6 minus secant 0. And that's going to be equal to 2 over square root of 3 minus 1. So secant pi over 6 is equal to 2 over square root of 3 because secant is equal to 1 over cosine, right? So that means that secant pi over 6 is equal to 1 over cosine pi over 6. Cosine pi over 6 is equal to square root of 3. So secant pi over 6 is going to be equal to 1 over square root 3 over 2. And then we're just going to kind of divide those two numbers or multiply by the reciprocal. So we're going to get 1 times 2 over square root 3, which is 2 over square root 3. And we kind of do the same thing for secant of 0. So secant of 0 is equal to 1 over cosine of 0. Cosine of 0 is equal to 1. So secant 0 is equal to 1 over 1, which is 1. Moving on to number 10. Now this looks like it might be a power rule, right? If we rearrange the function in this case. But it's actually going to be an ln situation. Since the exponent of x is a negative 1, the antiderivative of 4 over x is actually going to be 4 ln of x. So be careful of that. Power rule is probably one of the most common antiderivative rules, which is why I mentioned it initially before we started this worksheet. But just because it's the most common doesn't mean it's used every time that we have an exponent. And since technically our exponent here is -1, we do have an exponent, but the power rule is not used in this case. And instead, our antiderivative is going to be 4ln of x. We're then just going to go ahead and plug in 10 and 2, which is going to give us 4ln 10 minus 4ln 2. We can use our logarithm properties here, and that means that when we subtract logs, we can actually just go ahead and divide them. So we're going to get 4ln 10 over 2, which is equal to 4ln of 5. Now we're going to move on to a problem where we actually do have to use the power rule. So first we're going to rewrite the cubed root of x to make it easier on us when we're actually trying to do the power rule. So that's going to be rewritten as x to the 1/3 power minus 2x. And now we're actually going to take the antiderivative. So we're going to first add 1 to our original exponent. We're first going to deal with x to the 1/3. So we add 1 to 1/3, which gives us 4/3, and then divide by that new exponent. So our final antiderivative is going to be 3 over 4 times x to the 4/3. And then for 2x, we're just going to add 1 to the original exponent, so 1 plus 1 is 2, x squared. And then we're going to divide the original term by the new exponent, so that'll just cancel out this original 2 right here. And our final antiderivative will just be x squared. Then we're going to plug in 27 and 8. So just kind of a reminder, 27 to the 4/3 is going to basically equal the cubed root of 27 to the 4th power. So we always kind of want to deal with the bottom number of a fractional exponent first. So the cubed root of 27 is 3, and 27 to the power of 4 is 81. And then these are some pretty big numbers, so I'm not really going to kind of go into how I got them. If you are interested in putting this in your calculator, feel free to do so. But I'm mainly just focusing right now on the process of kind of taking antiderivatives, and not so much focused on adding and subtracting fractions and things like that. So negative 2,465 over 4 is our final answer. And then we're going to move on to number 12. So number 12 can be a little bit tricky, and it looks a little bit tricky, honestly. If you don't know that 1 over 1 plus x squared is a trig derivative. So if you've memorized your antiderivative rules, great. If you haven't, we can always reason this out kind of via reverse derivative process. So I'm thinking, what function's derivative is equal to 1 over 1 plus x squared? And the answer to that is going to be the inverse of tan. So we can deal with x squared using the power rule to find its antiderivative. And we're going to get 1/3 times x cubed, because we add 1 to the original derivative 2, which gives us 3, and then divide by the new exponent 3, and that's why we get 1/3 times x cubed. And then since the inverse of tan has a derivative of 1 over 1 plus x squared, 1 over 1 plus x squared is going to have an antiderivative of inverse tan. So that's going to be our antiderivative for number 12. And then we're just going to plug in 1 and 0. And that's going to give us 1/3 times 1 cubed minus inverse tan of 1, all in parentheses, that's top. And then we're going to subtract that by the bottom number plugged into the antiderivative, which is 1/3 times 0 cubed minus inverse tan of 0. And so that's going to end up equaling 1/3 minus pi over 4 minus 0 over 0. So the inverse tan of 1 is pi over 4, since the tangent of pi over 4 is equal to 1. The inverse tan of 0 is going to equal 0, since the tangent of 0 is equal to 0. So our final answer for number 12 is going to be 1/3 minus pi over 4. Okay, moving on to number 13. We actually are going to have a situation where our antiderivative will be ln, and also a situation where we need to kind of rearrange something so that we can use the power rule. So if you look closely at the problem, you see that we actually have two instances where our variables are on the bottom, and you might be thinking at first, maybe I need to rewrite both of those fractions. But if you think about it a little more, you recognize that 5 over x is an instance in which we should not at all rearrange the fraction to 5x to the negative 1, because since the exponent of x is negative 1, the antiderivative is going to be an ln, and we're not using a power rule. The exponent of x of the second part is x to the negative 2, right? So we actually can use the power rule in that case, and it would be good to rewrite that part. So we're just going to rewrite our integral to make it easier for us to use the power rule. We're going to keep 5 over x the same, but we're going to rewrite 2 over x squared as 2x to the negative 2, and then keep x the same. So our antiderivative in this case will be 5 ln x plus 2x to the negative 1 using the power rule, because negative 2 plus 1 is negative 1. And if we then divide by that new exponent negative 1, we're going to actually get rid of this negative in front of the 2 right here. So it's going to be a plus 2x to the negative 1. Minus x squared over 2. And that's just taking the original exponent of that final variable, 1, and adding 1. So we get x squared, and then just divide by that 2. Then we're going to plug in 2 and 1. And again, remember to put parentheses around your top component and your bottom component when you're writing these out. And I went ahead and just rewrote 2x to the negative 1 as 2 over x, just to make it easier when I do some math. So we're going to get 5 ln 2 plus 1 minus 2 as our top, minus 5 ln 1. ln 1 is equal to 0, so we can just replace that first term with 0, plus 2 minus 1/2. Which gives us a final answer of 5 ln 2 minus 5/2. So this last problem may seem a little tricky because it has like f prime of x, f double prime of x, but it's honestly actually more simple than when we have numerical and variable values that we have to kind of take the antiderivative of. I think it's definitely easier than the power rule. So we'll just hop right into it, and I'll kind of explain how to take the antiderivative of like just functions. The givens at the in the question we don't actually have to use until we're in the plugging in part, when we're plugging in the top number and the bottom number. But so first we're just going to take the antiderivative. So the antiderivative of f prime is f of x. And that's because the derivative of f of x is f prime of x. So the antiderivative of f prime of x is going to be f of x. That's just reversing the derivative like we've been doing this entire time. 7 is an instance where we kind of use the power rule. Technically, after the 7, there is an x to the 0 power. However, anything to the 0 power is equal to 1. So x to the 0 power would be equal to 1, and 7 times 1 is just 7. But now, when we're taking the antiderivative, we're going to add 1 to the original exponent of x. So 0 plus 1 is 1. And then dividing by 1 is just going to give us 7x. Now we're going to plug in, and that's actually where we need to use the givens in this problem. I've already gone ahead and replaced the f values just as their givens. But I'll point out where I've done that. So this 3 right here is f of 5, right? And that's right here, given in the problem. And then this -1 right here is f of 2, right? And that's also given in the problem. So as you can see, I've just gone ahead and replaced f of 5 and f of 2 with 3 and -1 respectively. Part B of 14 is very similar. We're going to first do the power rule on 2x, which is going to give us x cubed. Or sorry, x squared. It's going to give us x squared because we add 1 to the original exponent, which gives us x squared, and then divide by 2, which cancels out that original 2, which just leaves us with x squared. So the antiderivative of f double prime is going to equal f prime. And that's because the derivative of f prime is f double prime. So that means that the antiderivative of f double prime will be f prime, since we're again just reversing the derivative. And we just keep that 3 in front of it because it's a constant. And then we're going to again plug in 5 and 2. And I've also just gone ahead and replaced the givens in this case. So our first one will be f prime of 5. And as you can see, that's 4. So if we do 3 times 4, we're going to get 12. And let me move myself over here. And then we're going to have f prime of 2, which is -2 times 3, which will be a +6 right here. And that's equal to 3. So that's our final problem for this worksheet. And this has basically just been how to do integrals using FTC, using the Fundamental Theorem of Calculus. In our next video, we will use this to find the antiderivative at a point. And then after that, we'll talk about the second part of FTC. So please check that out if you're interested. If you enjoyed this video and found it helpful in any way, please give it a like and subscribe to our channel for more calculus videos. Thanks so much!